Hello? next presenter is Toge Højland Jørgensen, and he's going to talk about Bufferbloat and Beyond. Welcome, Toge.
Thank you very much. Yes, hello everyone. Thank you for coming. So the title of the talk is Bufferbloat and Beyond, and that's actually also the title of my PhD thesis. So I reused it so that I can reuse the template for the slides as well. So I'll talk a little bit about Bufferbloat. This is sort of the abridged version of the thesis itself. If after this you feel like you want to know more, I brought books. This is the thesis itself, so come and see me. It's first come, first serve. I have 5. But I'm going to talk a little bit about Bufferbloat. Show of hands, who've heard this before? Who knows what Bufferbloat is? All right. I'm going to tell you what Bufferbloat is, so don't worry, we'll get there. And then I'm going to talk about the work we've done in the Linux kernel to mitigate this, both on wired links and how you can fix your internet connection at home. And then I'm going to talk about Wi-Fi as well, because who here uses Wi-Fi? Another show of hands. All right, you're all awake. Thank you. Great. So Bufferbloat also affects Wi-Fi, and we've done some work in Linux as well to address this. And there's some policy work and some Airtime steering work that's also gone into the Linux kernel. And I'll give you an overview of where this work is today, and so on and so forth. But first, how many of you have experienced this before? And what do we mean when we say slow internet, and what does this have to do with Bufferbloat, and how does Bufferbloat cause slow internet? So usually when we say the internet is slow today, it's because we have to wait for something. It's usually not because it takes 47 seconds to download the big file instead of 44 seconds. It's more sort of, I clicked like on Facebook, and it took forever to light up with a little blue thingy, or I'm chatting and I don't get responses, I'm trying to have a video conversation and everything is laggy and I can't hear what the other person is saying. So it's all the interactive work. So it's really not so much about capacity and bandwidth, it's about latency, it's about getting an immediate response. And so Bufferbloat is basically this. This up here is a buffer, where, as you can see, the bottleneck down here is a little bit congested. There's more demand for capacity than this bottleneck can provide at the moment, so everyone just has to wait their turn. And this happens in networks as well. The timescales are a little bit different. In the network, it's milliseconds and seconds, whereas here it's, I don't know, probably hours. But it's basically the same effect. You have to queue to resolve this bottleneck. And that turns into latency that you have to wait for. And this happens wherever there's a bottleneck in the network. Usually when you have your home network at home, the bottleneck is actually your router that connects you to the internet, because the internet connection is slower than what you have inside the house, so that becomes the bottleneck, and then you get queuing. To put it another way, this is why I have cute, blocky 8-bit animals on the title of this. This is an elephant, as you can all plainly see. This comes from the term we talk about elephant flows. So an elephant flow is this big lumbering download, or it's your BitTorrent connection, or it's your cloud backup that runs automatically in the background, transfers a lot of data. It's slow, but it will get where it's going eventually. It doesn't really matter. Latency is not so important for this. So as I said, like if it's a few seconds extra to download your file, it's probably not such a big deal. But we also have mice. And the mice is all the interactive stuff. It's your DNS lookups, it's your ping packets, it's your VoIP flow, it's your SSH interactive connection. It's all the stuff that you actually care about as a user when you're using the internet. And as you can see here, this is the information superhighway. And the elephant, there's only a single lane, so the elephant is blocking the path, and the mice has to wait behind him, and they get really annoyed. So what can we do to this? About this? Well, fortunately, we have our friendly penguin. You've probably seen him before. It's Tux, the Linux mascot. So as I said, most of the work I've been doing with Linux. So what we can do is we can get Linux installed in the router that has the bottleneck, and we can make sure that we do something smarter than just having this single connection. And then we get something like this, where the penguin stands here at the bottleneck and guides the mice around the elephant so they don't have to wait. I'll get back to what this actually means in terms of algorithms and so on. So this is the basic concept of Bufferbloat and why it's bad and what we need to do about it. To turn this into numbers, this is a graph from a test tool that I wrote while I was trying to look at this. What you see here is the latency of, it's a ping flow, basically, between two endpoints that are like back-to-back Ethernet connected. So the baseline latency is basically 0, a few milliseconds, or like point-something milliseconds. And then after 5 seconds, we start up a big TCP download, the elephant flow. And then you can see what happens is that our ping flow, the different colors are different ping flows. We have UDP ping flows, we have ICMP ping flows, all this kind of stuff. The latency climbs up to 800 milliseconds. So these are the default settings in Linux before we started fixing this. So it's a FIFO queue of 1,000 packets, and that translates to, in this instance, 800 milliseconds of delay, because I think it's like 20 megabit per second connection or something. I forget the numbers. But this is a lot to wait for every packet that has to go through. And that's really noticeable as delay, and it completely kills your VoIP. So what can we do about this? This is a figure from a paper written by Van Jacobson back in around year 2000, I think. And he used this illustration to illustrate a servo system. So the way the internet works is a lot of the traffic is run over TCP, or these days QUIC, but that does something similar. So for these purposes, it's about the same. So TCP is a feedback system where the sender will send out data, listen for the response, and it will do retransmits if something is lost and try to adjust its rate to the actual capacity of the internet. We do this because when we start sending packets over the internet, we don't actually know anything about the available capacity, so we have to probe. And so a TCP flow becomes a servo system that tries to adjust itself to the available capacity. And that's sort of, this was just an illustration, and actually the paper was rejected because some of the reviewers got offended that someone would put a picture of a toilet into a scientific paper. So it never got published. And that's part of the reason why we still had this problem, well, 5 years ago now. This servo system means that TCP reacts to losses on the path and say, okay, a packet got lost, that's probably because I exceeded the available capacity, so I have to slow down. And if there's a large buffer, a queue in the internet of 1,000 packets, packets are going to get delayed, they're not going to get lost, so TCP is just going to keep sending, and it's going to keep increasing its rate and exponentially until it does overflow, at which point we're back to the 800 milliseconds of delay we saw before. So what we can do instead is we can do this thing that's called AQM. So AQM is short for active queue management, which means instead of just having a queue, let's actively manage it and do something about what happens. So CUDDLE is a new algorithm that Van Jacobson also developed along with his wife, Kathy Nichols. And it's quite simple. This is actually all of it. This is the queue. It's k packets long. It can be as long as you like, actually, because, as you'll see, it will rarely get filled up. So what we do is a packet, the blue things here are packets. When a packet comes in, we timestamp it. And then it goes into the queue, and we just dequeue packets at the rate that the link can service. And every time we dequeue a packet, we say the timestamp of the packet, how long ago was that? Is that more than 5 milliseconds ago? Well, then we started building a queue. And we don't want that, so after 5 milliseconds, we say, okay, now we have a queue. Then we drop a packet. So we don't do this immediately. We wait for one RTT. We wait 100 milliseconds. Is it just like, was it just a queue that arrived and then it immediately drained again because there was a transient spike? That's fine. This is what queues are for. But if it stays there for too long, then it becomes a bad queue. It's a standing queue and it just adds delay. So if after 100 milliseconds we still have more than 5 milliseconds of delay, we will drop one packet, just a single one. And then we will wait another 100 milliseconds because the drop signal then has to travel all the way to the receiver of the TCP connection, which then sends due back to the TCP sender saying, this packet is missing, and then the sender slows down, and then the queue will drain. And this takes around an RTT because the signal has to go all the way around. So hopefully, if this works after one RTT, which we just pretend that's 100 milliseconds because we'll tune, I'll get back to that. Then hopefully the queue will drain and we're fine, and we can keep the queue at a very low level. But sometimes it's not enough. So if after 100 milliseconds we drop the packet, nothing happens, we drop another one. And we have a counter of how many packets we dropped. And we keep increasing this, and we so divide the interval that we take between drops by this counter. So the more packets we drop, the more frequently we start dropping packets, until eventually we find the real RTT and the real rate that we need to drop packets at to keep TCP sort of adjusting. It will keep adjusting its rate up and down. And this turns the feedback loop back into a well-tuned machine that will oscillate around the bottleneck capacity, which is good. So now we can utilize our link, and we can get low delay in the queue. So this works fairly well. Cuddle itself will get you down to, instead of 800 milliseconds, you can get down to 10, 20, depending on how many flows you have and so on. But we can do another thing as well. We can do fairness queuing. So this is SFQ. That's been in Linux forever. I think Paul McKenney came up with this also back in the 90s at some point. So the idea is, we get in the packets here, the different colors are different flows. So a flow is like a hash and the 5-tuple, so source and destination IP, source and destination port, and the IP protocol number. So TCP and UDP are two different things. We hash them, and then we give each flow, like the different colors, now get their own queue. So this, and then we just do round-robin dequeuing. So we get one packet for each flow at a time, and then we go around. So this means even though this guy has a much longer queue than this guy over here, if they were all in the same queue, these two packets will have to wait for all 5 packets of this flow, but now it only has to wait for 1 packet from each flow. So that means each flow will get its fair share, and if one builds a really long queue, that only affects itself, it doesn't affect the other flows so much. And then we just do the cuddle thing we did before. We then apply individually to each queue. So if this flow only has 2 packets, it will probably not be 5 milliseconds. But if this flow has a lot of packets, it will hit the 5 millisecond target of cuddle, and it will get a drop, and then that will be the signal to slow down. So we can actually more accurately target the flow that we want. That's the basic fairness queuing. And then the algorithm that we actually use now, which is, it's not the default in most Linux distributions. So if you have a Linux server, you're probably running it. It's called fqcuddle. It's a QDisk that you install in the Linux system. It does the same thing as SFQ, but it adds an additional mechanism, which is called the sparse flow optimization. So we do the hashing from before. We have all the different flows. We hash into different hash buckets, which each gets a queue. And then once a new flow comes in, arrival here, new packet comes in, we hash, we find its queue. This becomes new. So it's a new flow. We don't have state for it. We don't have a queue with packets in it. Then once it gets dequeued, once we dequeue a packet from this, either there was only this one packet and it gets exhausted, or it uses up all its credits, so it goes one time through the round-robin mechanism. It goes out to old, and then it just stays here until it empties out and comes back. So that means we can keep track of flows that we've only recently seen. That means flows that send at a low rate. And then what we do is we simply give the new flows priority over the old flows in the different, like all the different queues. So these queues, all the new queues get dequeued first. So that means new packet comes in, this could be, for example, your DNS request that you want to answer a quick answer to, because then you're going to do something else. It can also be your VoIP packet, because that is not using a lot of bandwidth, actually, your gaming packet, all these kinds of things. It'll come in, it'll get priority, it'll go out, and will have 0 latency. I'll show you graphs of this afterwards. So this is it's actually like 5-10 lines of code to do this. And this just means that you magically prioritize all the traffic that is latency sensitive. There's no QoS, there's no diffserv, there's no marking, there's no policy. It's just 10 lines of code in the queue list. And this gives amazing results. So these are the results. This is a bit of an unusual diagram, so I'll explain it a little bit. This is the output that the flow gets in megabits per second. This is a 10 megabit per second link, so minus headers and so on. This is about the rate. And then this is the induced latency, so the additional latency over the baseline of this experiment. And so each dot is the median value for all the different queuing algorithms that we used. And then the size of the ellipse is a measure of the variance of the measurements. And so FIFO fast up here, that's the FIFO queue, the default Linux queue list before we start doing this. It's actually a limited version. The default FIFO fast has a 1,000 packet queue. We had to limit it because otherwise it would be like out here or where I'm standing. So this is like, it'll be 10 times worse if it was the default 1,000 packet queue, but still it's quite bad. It's like 100 milliseconds of added latency. This is just cuddle that I explained before. Pi and A-rate are 2 different AQMs that sort of similar to what cuddle does, just a different mechanism. And then up here we have all the queuing, the Fanish queuing. So SFQ is out here, so that in itself, just round robin, gives quite a lot of benefit to the ping flow. And then FQ-cuddle has the sparse station optimization that I just explained, and now we get down to, like, it's basically hitting the margin. You cannot see that the download is here. And FQ-cuddle went into Linux 3.12, I think. So it's been there for quite a while. It's become the default. Systemd changed the defaults in the sysctls that they switch. OpenWRT, the router distribution, has had it as a default for years now. So when you turn this on, it just sort of works, and you will get no latency, almost. So there's a few caveats. I'll get to those. Thank you. We then did pieces of cake. So we did another queue list that's called cake, which does the same thing as FQ-cuddle, but then it adds a few other things. One thing is traffic shaping. I'll come back to why that is important. Then it does host-based fairness. So the FQ-cuddle thing gives you a different queue for each flow, which also means that all flows will get the same bandwidth. So if you open up 10 flows, you'll get 10 times as much bandwidth. And depending on your network, that may or may not be a good thing. So if at your home, maybe you want to limit the different devices to get the same thing, and with Cake, you can do this. So like, this is just per flow fairness. Then you can say all the different destinations should get the same. So the three C flows gets the same share as each of these other flows, and you can limit by source, you can limit by both, and FQ-cuddle is over here, it's the same, just fairness flow. Then we added diffserv handling in Cake as well, so there's a reasonable implementation of prioritization based on diffserv markings. And there's ACT filtering, because if you have a really asymmetrical link, you can actually get to the point where you cannot use your downstream bandwidth because all the TCP ACTs that are coming back in the other direction do not fit through your bandwidth. I think this happens around a ratio of 20 to 1. So if you have a 20 megabit down, 1 megabit up, you cannot use 20 megabits with a TCP flow at all. It's impossible due to the way TCP works. But we can filter these ACTs, and that means we can actually use this again. There's more details in the book if you want these. But the reason I said that traffic shaping is important is because we have this feature called byte queue limits. So unfortunately, the Linux kernel is a complex beast, as are all systems, and there will be queues at different layers. So we have the queue list layer, which is where we can install all the smart handling, which is nice. Oh, I love the weather here. But there's also different queues. So we want the... Can you still hear me over the rain? All right, great. So we want to be able to install, when we install a queue list, we want it to actually manage the real bottleneck queue. So we want to limit the queuing in the lower layers. And there's another layer, there's another queue in the hardware as well. So, so for Ethernet, we have this thing called byte queue limits, which is enabled in most drivers. So what that does is it sort of dynamically keeps the queue in the hardware as small as possible so that the hardware doesn't starve. It's fairly simple. It sort of increases or decreases until the hardware starves and then increases a little bit. And it will keep the queue small so that we can control it and have the actual, oh my goodness, queue in the queue list layer. It's a pretty small patch. If you have a driver, do it. But other technologies such as DSL and so on do not have this generally. So your DSL modem that you get from your ISP, or if you are an ISP, which I know some of you are, you buy a DSL router, and the DSL connection doesn't have this, so just turning on FQTotal is not enough. And so the real fix is to go and fix your driver, but this is not always possible because you can have proprietary firmware, you can have proprietary drivers, you can have vendors that don't have a clue. So what we did with Cake is we can do a shaper, a software shaper, in the queue list, where you just tell it what is the actual rate of the underlying link, and then we shape the capacity, or we pace out packets so that we never hit this rate, and that means there will never be a queue in the hardware. We can keep it where we can control it instead. And having that inside Cake means it's a lot simpler. It's like one line of config to turn it on. Right, Wi-Fi. How many remember these? Awesome. So this was the first, I'm not sure if this is actually the first edition, but this model, the Linksys WRT, was the first Linux-based access point. And Linksys shipped this running Linux. And then there was, when they did this, they were not really aware of the GPL, or maybe they, I don't know. They didn't release source code, but there was, lawyers got involved. There was a lot of legal action, and eventually they were convinced to release the source code. It was just sort of a source code dump. There was no community or anything, but people ran with this, and that's what we have now in OpenWRT. And that has gotten so popular, it's so good, that probably all of your home routers are running Linux in one form or another. So if you're not doing what we're doing at this conference, as far as I can tell, like running enterprise access points, all the consumer stuff is probably running Linux. So that means we can also go and poke at Wi-Fi. And if we go back to the same graph I have before, but this time it's over Wi-Fi bottleneck. So once your internet connection gets above 50, 100 megabits, depending on conditions in your home, the Wi-Fi link starts becoming the bottleneck. And lo and behold, Wi-Fi also has problems with queuing. So this is the same graph, but with a Wi-Fi link as the bottleneck. We install FQTotal. It still helps a lot, but we are now at 100 to 150 milliseconds instead of 0 milliseconds of queuing. And as you've probably guessed, that's because there's another layer of queuing at a lower level. And we don't have BQL for Wi-Fi, and we can't just use BQL because the Wi-Fi MAC is a bit weird. So Wi-Fi has a lot of overhead to send a packet because it's unmanaged spectrum, so you don't have a controller saying you can send now, you can send now. So basically what a Wi-Fi device does is it goes back to the original Aloha protocol. It's like listening, is anyone transmitting? No? Cool, I can send something now. So every time you can transmit a packet at Wi-Fi, there's a lot of overhead where you have to wait and you have to figure out, can I transmit now, and so on. And you can only do it to one, if you're an access point, you have to do this individually for each station you're trying to transmit to. And then we added, because this is very inefficient, the reason why 802.11n is more efficient than 802.11b and g, and why 802.11ac is even more efficient, because we added aggregation. So instead of just sending one packet every time you've done this whole listen dance, you can send a whole bunch of packets. For 802.11n, it's 64K. For 802.11ac, you're allowed to send up to 4 megabytes of data in each transmission opportunity. And that means you need to have all this data ready to go when you get the chance to send. And this happens on microsecond timescales. So it's too late to go up and ask the operating system, oh, I'm ready to transmit now. Please send me 4 megabytes of data within the next 4 microseconds. That doesn't work. So we need the queuing to be different. We need to have packets queued up for each station ready to go. And that is these 100 milliseconds. The drivers did this. For some devices, it was the firmware. This is AF9K, so everything is in software. So the driver had this queue per station ready to go. So we had to change this. We have to fix this. So we did this. This is the Wi-Fi queuing stack before we started changing it. So this is the queue layer I was talking about. Up here, you can install FQCuddle. Yay! And then you have all this stuff down here. This is the driver. You have a per station queuing, and there's a retry queue, and there's all this round robin and aggregates and all this stuff. And that's the 150 milliseconds. And so, as you can see, this is obviously way simpler, right? No, but what we did was we moved FQCuddle down here. So this is still here in the driver. That's a retry queue, but it's usually empty. Usually you don't get that many retries. So usually you just have this up here, where we can do the FQCuddle dance, we can get all the per flow queuing, and we just replicate this per station. So there's like 8,000 queues, and we just divide them out and so on, and that's fine, it's just software. And then the hardware just has 2 aggregates ready to go. So this comes down to 10 milliseconds now. And like, it's always nice working with this stuff. A lot of times you have to use a logarithmic scale, as you can see here, because otherwise before and after won't fit in the same graph, which is kind of cool. So we went from the 100, 200 milliseconds down to 10, 20 milliseconds of delay over Wi-Fi when we did this. Another thing this actually does is because before here, this was actually a pretty small queue. There's only 123 packets in total we could queue down here. So the total queue space actually increased, but because we're managing it, that doesn't result in big latency, but it means that we can have more packets ready to go. So if you look at the throughput here, you will also see, even FQCuddle helps a little bit, but FQMac, that's just the fairness queuing, the diagram before. I'll get back to what airtime means. But this increases throughput for fast stations because we can build bigger aggregates because we have more queuing space. We have more packets ready to go. And for slow stations, that decreases throughput. I'll come back to that, but it means that the aggregate throughput of the whole network increases because the fast stations can now go faster, which is good. But we have this thing in Wi-Fi where airtime usage is really the sparse resource. It's not bandwidth. Like, it's the time you spent transmitting to different stations. And how can we control that? So there's this thing also back from like 10, 15 years ago called the 802.11 performance anomaly. It was described the first time for 802.11b. So this just says that if you're fair in transmission time, which is what we want to be, everyone on the network should get the same amount of transmission time. That means TI, the time you spent transmitting, should just be 1 over the number of stations. But if you don't have fairness, if you're just using the Wi-Fi MAC, because every time you transmit, you're listening, and there's a random backoff, and then you get to send maybe. So everyone gets the same probability of sending, but not everyone spends at the same time. So if you're sending at a very low rate, that is like you're speaking really slowly. So it takes a lot of time to send the same amount of data. So you will actually spend more time transmitting if you're transmitting at a really low rate. So that means that your time spent transmitting is now the throughput fairness. You get throughput fairness. So it's dependent on the rate of the other, your rate relative to the other stations in the network. And this is bad because that means if you have your phone, like if someone is sitting with their phone at the other end of the house, far away from the AP and trying to watch a video, they will have a very low rate, and that will hurt everyone in the network. So what we want to do is we want to change this into airtime fairness. And it turns out that if you're the AP, you can actually do this by just keeping track of how long time did you spend transmitting to each station, and then even that out by just scheduling them differently. So if I send to you, and that takes me 5 seconds, and I send to you, and that only takes me 1 second, millisecond, then I'll send to you 5 times before I go back to him, because he's the slow guy, basically. So it's just a round-robin scheduler. It's actually the same mechanism that FQCoddle does for flows. We just do it in the time domain. And we already have the per-station queuing, so it's just a matter of scheduling which queue. And we have to do some scheduling, so we might as well do round-robin scheduling with this as well. So we changed the Ath9K driver to do this. And before, with the FIFO thing here, you saw this is the slow station. It takes out 90% of the airtime, and these two get almost nothing through. And then, as I said, this gets a little bit better, actually, with when we change the queuing already, because we can make up for it a little bit by sending bigger aggregates to the fast stations. But if we do the actual scheduling, we can get complete fairness between all 3 stations. And this scales up to, with the test up to at least 30 stations, and a single AP just scales. And then we go back to the throughput we set before, where airtime now we get the fast stations get more data through because they now get their fair share. It hurts the slow station a little bit. And if you want to fix this, I'll come back to that, because that was, when I first presented this, the first question was, what if I don't want fairness? What if I want something else? So we went back and we did policy as well. But for just fairness, this is the aggregate throughput. This is the average of all your stations on the network. So this is sort of the aggregate throughput for your whole network. You get a more efficient network. You can transfer more data on your Wi-Fi network, which is nice. So, policy. The first reaction I get, but what if my TV is the station that's far away from the AP and I want to stream to that, so it should get all the airtime it needs? It's like, okay, let's try and do a prioritization thing where we can prioritize single devices. Maybe we want to balance device groups. In 5G, it's all the hype. There's this thing called network slicing, where the operator wants to sell their resources as many times as possible. And then if you're a BMW and you have a fleet of cars and you pay extra, then you can get priority and you can get reserved a certain amount of the airtime. And they can do that on like LTE and all these technologies. It's easy, but on Wi-Fi, we also want to do this. So this is also a way you can do this with the same thing. It's not my favorite use case, but it's something that's possible with the same mechanism. Or you can do this other thing, which I think is way cooler, if you want a maximum capacity. So you have an open guest network, and you don't want to sort of set a set limit to someone. Like if no one is using your normal, regular Wi-Fi network, why shouldn't the guest network just be allowed to go? But you can limit it to a maximum capacity. So you say the guest network cannot take up more than half of the transmission time that this AP is going through, no matter how many stations are on it. And so the way all this is implemented is we just have a daemon. It's actually in host APD now. That just polls the kernel and say how many stations are active. Do they have a queue? OK, if they have a queue, that means they're probably transmitting. So there's these many stations, and I want my group to have this share. So I just divide that by the number of stations, and then I put weights into the kernel. And then the kernel just does a weighted scheduler, the same way as before. And then you can get these different operating modes. So you can say just static mode, my TV needs priority, or different groups needs the same weight, or different groups needs to be limited. So just configure the daemon to this, and it'll just keep listening to one station's associate and go away, and when they stop transmitting and so on. And this works pretty well, actually. So here we have the purple station should get half is on the guest network. Or like the home network, you should get half. This is one group, and the 3 others is another group. So this group should always get half. So in the beginning, it has all the time to itself. Then one station comes on, and now they share. But then another one comes on the guest network, and the guests together get half, but the purple one still gets its half, and so on. Or you can just say everyone shares equally, and then they will immediately share equally as they come on the different stations. So, as of kernel 5.1, which is now already 2 releases old, everything here is now upstream in Linux. This is the history. So I was actually wrong when I said 3.12 for F2 throttle. It's all the way back to 3.5, which is like 2012 or something. BQL is even before that. Shared Cake has been living out of tree for a long time. We finally upstreamed it last year. The Wi-Fi queuing stuff got in 4.10. 4.11 is Airtime fairness for Ath9K. Then we spent a lot of time doing the policy, and we also ported all the Airtime scheduling from the driver to the common MAC 802.11 framework. So by 5.1, that is also upstream in the kernel. I still have to post patches for OpenWRT to be able to configure it, but that's a minor detail. So all is good, right? We fixed Wi-Fi, yay, except drivers. So Ath9K is amazing. Ath9K is this open source driver from Qualcomm Atheros for 802.11n networks. It's completely open source. It's written originally by Felix Feetkow. It's an upstream developer. And you can do anything with it. Like the hardware is really dumb. So all the handling is in software. So that's been the prototyping platform of choice. If you go into Google Scholar and put in Ath9K or Ath5K that came before, you get thousands of hits. Ath10K is then the follow-on for 802.11ac. And unfortunately for Ath10K, they decided to move a lot of the functionality into firmware. And the firmware is closed. It's a binary blob. You just get it from Qualcomm. It crashes all the time, and it's really horrible. So we could do some of it. I'll explain this in more detail. MT76 is better. It's MediaTek 802.11ac, but the hardware is not as prevalent. IWL, Intel Wi-Fi, just added this quite recently for the Wi-Fi queuing, but doesn't have Airtime. But it's not so important because it's mostly clients and so on. But others, most notably Broadcom, is a lot of CPE you'd get at home, but all the other vendors, nothing. Some of them, we could get it into the driver, but again, we have this problem with a lot of the logic has moved into closed binary blobs firmware, and that's really bad. But we have some ongoing work to try to alleviate this a little bit. There's this thing called air queue limits. Remember I mentioned BQL in the beginning, byte queue limits? Well, for Wi-Fi, we can sort of do the same. If we have a big, dumb firmware blob that will queue a lot of packets, Ath10K, for example, will do seconds of queuing, thousands of packets. But we can do the same thing that we do for BQL, except for Wi-Fi, we had to account in time, not bytes, because the whole transmission time thing. But we already know, sort of, usually, roughly what time, how much time, or what rate we're going to transmit to each station, so we can go back and calculate bytes, and then we can put in limits, and Google prototyped this fast 10K with great effect. But unfortunately, it is open source. It's in Chromium, but they implemented it in the driver, so it needs a bit of porting work to go into the framework that we did upstream. But that will help a lot on the queuing side. Airtime fairness might be possible as well. It's actually in Ath10K, and it works fairly well, but for other hardware, it sort of depends on how it works and so on. Yeah. So, and then there's also when we changed the queuing stuff in MAC 802.11, drivers have to opt into this. So it's a different API between the driver and the rest of the kernel. And there's some, Johannes, the Wi-Fi maintainer, Linux has some idea to just emulate the old API, and then we can just port everything at once instead of having to port every individual driver. And then there's and then we just, for getting the AQL support and for getting airtime fairness, the hardware needs to be able to tell us how much time did I spend transmitting. So that's why I say it's not necessarily all drivers we can do this with. What you can do, if you're someone who purchases a lot of devices from an OEM or something, is you can go beat up your OEM, and they can go beat up their vendors, and maybe we can actually get support for this. I know it's an uphill battle. It's really annoying, but if you can actually get support, if you can pick hardware that has support, this really helps the Wi-Fi experience. It gets a lot better. This is not so important. That's sort of another thing that's ongoing is this virtual time-based scheduler. So specifically when we try to do MuMIMO, or because it's DRR-based, we have to throttle, like you do round-robin scheduling to achieve airtime fairness, so you have to throttle stations quite a lot if they're slow, which can be a bit difficult. Or like it can get you some weird delays. So we have this prototype patch to use a different scheduling mechanism, which I have to go back and brush off and send again, which might improve this. But it's sort of a more of an implementation detail than its functionality. So, summary, Bufferbloat. Now you know what it is, why it's important, and how to get rid of it. It's basically fixed in Linux for a lot of the technologies. You can fix your own home networks. The network you save might be your own. Go do it, especially if you happen to be at an ISP and you can do this for all your customers. We have the technology, like Cake is one line of config to turn it on your router. We have scripts, it's an OpenWRT, there's a GUI, you can just turn it on, it really helps. The internet works again, it's amazing. You can have your video calls while you're running BitTorrent and downloading and everything, and you don't notice, it's amazing. References, these, the blue stuff is links. I don't know if the slides are going to appear somewhere, hopefully, so you can click on these. If not, you can come get a book from me. If you want to know more details of this is also, most of the research is open access, so you should be able to find it on the internet if you want to read the gory details. So yeah, thank you.
So, any questions for Torge?
Hey, how does your work tie in with environments where you have lots of other APs going around, sort of taking up airtime and so on? Do they respect these changes, or how does that work?
Yeah, not really. The AP only looks at the traffic that it sees. So if you have an environment where you have a lot of other APs, if they're in different channels, it doesn't matter, they don't interfere. But if you have interference on your own band, whether it's another AP, it's LTE, it's a microwave, whatever, this just means that the amount of airtime that you get for your network decreases. You'll still be fair within your network, but the overall capacity will decrease. I've seen someone trying to do a coordination daemon. If you control all the access points, you can install software that will communicate between them and try to sort of slice out the airtime between the APs by sort of, to ensure fairness across the whole network. They're in Spain. They had a prototype that was using a different mechanism for enforcement, and then they said maybe they would port it to just use this, and then so it's just a coordination between access points, and that's possible because you can program host APD to set the weights differently to just slow everything down, kind of. And also the schedulers, they're all work conserving, so it'll divide out the airtime you have, but if you don't have it, then you don't have it.
Anyone else?
So the Cake scheduler, is that only for the Wi-Fi interface where you are running as an access point, or is it for also your laptop?
Actually, Cake doesn't work so well on Wi-Fi because we needed the queuing per device. So all the stuff we did on Wi-Fi was try to get the Wi-Fi queues themselves to work, so we don't have to do it at the queueless layer. So the main use case for Cake is your upstream connection to the internet. So it's like where usually you have some hardware that you can't control. Either it's because you have an ADSL modem or something from your ISP that's just a black box, and it usually has a big queue. So what you then do is you shape to rate just below the bottleneck, and then you can move the queue to where you can control it. And Cake is really optimized for this. It also has features to compensate for different framing. So DSL will split packets up to small AQM cells, and that has to be taken into account when you're shaping and so on. And on the other direction, on your home network, you can try to shape after the bottleneck. You have to shape a little bit lower, but because it's TCP, you can sort of influence it as long as you're not being DOS'd. So you can sort of fix it in both directions from your CPE. But Cake is really its target audience is fixing your home network. Maybe using it as an ISP as well, but there's some features missing a little bit for this. But could presumably be used for this as well.
All right. So say you have a really fast fiber connection and you just want to optimize your Wi-Fi, then FQ-Cuddle would be fine.
Then you would, if you just want to fix your Wi-Fi, then you find a Wi-Fi device that has driver support for the Wi-Fi stuff and use that. Then you don't need to do anything. Like actually, you will see if this is the AQM stuff in the Wi-Fi driver is activated, we remove the queue disk completely. So you will get no queue on your device, and all the queuing happens inside the MAC layer for Wi-Fi.
Anyone else? No?
Oh,
Then
and
let's
also,
skip. Yep.
oh, sorry, just because you have a fast fiber connection, you can still have Bufferbloat. So you should measure and test.
Yeah. So let's give Toga a big hand.
Thank you. And if anyone wants a book,